Hello, this is Anything Today. We're solving some questions on Folland real analysis. First thing we'll solve is question 2 point, just a minute, where is it? 2.8. So the question is, if f is monotone function, then f is Borel measurable. And for the proof, without loss of generality, we assume that f is monotone increasing. This is because if f is, monotone decreasing, then, we just use f minus f, and this will give us, again, monotone increasing function. So, and as we know that the measurability is close under multiplication, this still holds. So we just need to show one case. So we'll just assume that f is monotone increasing function, or you could just say non-decreasing functions, doesn't really matter much, but yeah. Then since we are showing that f is Borel measurable, we'll show that sorry about this, I only use pink, so f inverse of a infinity is indeed measurable. We'll show this, and the proof will be done for all a. And the way to show it is, on second thought, I'll just go for this half closed interval. It doesn't really matter because they all generate the Borel measure, so we just need to do anything we want. And we're going to say that define S to be an infimum of x such that fx is bigger than a. And this will show how the proof is done. If this is empty, then the proof is trivial, because empty set is also a Borel measurable set, so it doesn't really matter much. So we're just going to think that this inverse set is not empty. So then, because we define S to be an infimum, we know that for any x bigger than s, we're going to have fx bigger than or equal to a. This is the definition of the infimum. And if it happens to be a case that fx is, not fx, if fs is a, then the inverse of what we defined earlier is just going to become from s to infinity. And this is Borel measurable, then the proof is done. And otherwise, if it's the case that fs is smaller than a, then this inverse is going to give us an open ray, which is again also a Borel measurable set. So since in either case f inverse gives us a Borel measurable set, the proof is done. This shows that f is a measurable function. So that's the proof for 2.8, yeah. And we're going to also prove proposition 2.11. And 2.11 is made up of two set of statements. The first A is, sorry about that. If f is measurable and f is g for mu almost everywhere, then g is measurable. Just for simplicity, I'm just going to write ms for measurability. from now on. So show this is not that hard. So, oh, and in this part, we're just assuming that the functions are real valued function. I mean, it could be complex value. It doesn't really matter much because all we need is the range space to be some set either R or C so that we can use Borel measurable sets. So we're just going to assume that's real valued. And the mu is also, we're going to assume that mu is a complete measure for this to hold. Then let be some set in R. To be exact, is a Borel measurable set. Then G inverse of B. This becomes G inverse intersection with E. And this plus G inverse with E complement. And E, what I'm going to tell you what the set E is supposed to do. Because we assume that F equals G mu almost everywhere in a mu sense measure. So they're going to be set E such that F is not G in E, where mu E is 0. So F is not G only in a measurable set where its measure is exactly 0. So using the fact we divided G inverse B into this formula, and this becomes, well, G inverse B with A, and is F inverse B subtracting E. And, well, we know that F is a measurable function, though, so this is measurable. So this is measurable by definition, and E is a measurable function, so this part is a measurable function. And we also know the fact that mu is a complete measure, and we know that mu is 0. And remembering that G inverse B intersection E is going to be a subset of E, and the measure of E is 0. Measure of this is going to also be 0. And we also know that this is measurable because this is a subset of a measurable set where the measure is 0, and in a complete measure, every subset of null set is measurable. Is contained in the domain of the sigma algebra defined in the complete measure. So this is going to be 0. So this is going to be 0. And since both parts are measurable, the whole union is going to also be measurable, indicating the fact that G inverse B is in fact measurable. And that ends the proof. The second part is a bit more tricky, but it's more easier if you use the result from A. That is, if Fn is measurable for all n, and Fn converges to F mu almost everywhere, then F is measurable. Well, we can easily solve this using the result from A. That is, we also already know from a previous proposition that if we define F, how to call this? I'll just use the notation that I know how to pronounce. So F tilde is a lim sup Fn, and we already know from other proposition that this is measurable. This was in 2.7 proposition, so just remember that. So, as we know that Fn converges to F mu star almost everywhere, and considering two parts of this, we know that F tilde is equal to F mu almost everywhere. And since we already showed in A that this means that they're both measurable, so we know that F is going to be measurable, because we already know that F tilde is measurable. So that's the end of the proof. Well, that's it for today, and thank you again for coming in to